Yeah. Connect. Yeah, I think it is connected. In the phone. Just like not this one, this one, and this one. This one's wait, and then this one. Yeah. So now, for this, after you have checked, that's when I'll give you a report. That report, if there are changes, you can make changes. If there are no changes, it's okay. Okay, today or tomorrow? No. By tomorrow, I'll give you back. Even today, once I'm just done with the class. Okay. Let me just greet these guys and start the class. Okay. Okay. Good morning, students. I hope you're able to hear me. Please, you can just start. I'm almost about to start. Please, good morning, everyone. So that I can start. Once you respond, then I can start the class. Good morning. All right, can I start the class now? Okay, that's wonderful. Someone has started to say I can start. Okay, so today we are looking at the other methods of integration, which, like I mentioned yesterday. So today we have to finish integration because, as you can see, we've run out of some extent time. So we are looking at integration by parts as one of the methods. Uh, uh, that is integration by parts method. Now, integration by parts. So what happens in most cases when we are solving any math problem which involves calculus? So what happens is that there are some questions that using substitution, any of the methods of substitution that we learned yesterday, whether using trigonometric substitution, whether you would want to use the algebraic substitution, or you want to use the identities, you discover that you can't manage to arrive at the answer. So you try this way, but the integral part is not becoming at any point simpler to evaluate, or rather to simplify. So then if that case arises, what you can do is you can use integration by parts. But before I go to integration by part, if we recall that if we have two functions f and g which are differentiable, these two functions f and g are differentiable. If these two functions are, you are able to find their derivatives, then f, the product is also what? Is also differentiable. So if you have these two functions that you are able to differentiate, then their product is also what? Differentiable. And the derivative, so basically, and the derivative with respect to x of the product, which is and the derivative with respect to x of the product, which is f of x times g of x, we said this is equal to, okay, this is what we said, this is equal to f of x times the derivative of g of x plus um, plus g of x, the second function, times the derivative of the first function. So this is what we mentioned last time. This is what usually goes on. Now, the question here is, what happens when we differentiate. So maybe let me put it in a simpler form. If you look at this expression, we can also rewrite it. We can also rewrite it in this form. So this expression you are seeing here, we can also rewrite it as f of x, g, the derivative of g of x plus g of x times the derivative of f of x. So we can do that. We can do that. We can also do that here. We can put dx. I hope everyone is following. Then times okay, sorry, supposed to do that, which is equal to the derivative of this function. Yeah, we're supposed to put dx here. So dx, which is equal to the derivative of the function f of x times g of x. Okay. So this is what you're going to have. Now, if we integrate both sides, so if we take, or we say taking integrals both sides, if we take the integral both sides, what we have is, so if we take, we are going to have the integral of the function f of x times g of x prime, okay, plus g of x times f of x dx. Now, when you take the integral on the right hand side, what you're going to have on the right hand side, you're going to have f of x times g of x. This is what you're going to have. So now, using the linearity property on the left hand side, we can split this. This we are going to have the integral of f of x times g prime of x plus the integral of g of x times the derivative of f of x dx. We're supposed to have dx here plus this is equal to f of x times g of x. I hope you're able to see what I'm explaining. Please make sure that you're able to see what I'm explaining. Okay, now we can rewrite the whole of this function. We can rewrite this equation, and then on the left hand side we remain with the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of g of x times f prime of x dx. Okay, so this formula you've seen here, so we can just say rearranging gives that. So this formula here, maybe I can put this formula to be star. So the formula star is the formula for integration by parts. For integration by parts. So this formula is the formula for integration by parts. Now, is that, let's look at this formula now. If we don't want to put it in this form where you have the function f of x, g of x prime, f of x times g of x minus the integral of f of g of x, f prime of x dx, we can do this. We can substitute those by letters such as u and v. So we are going to say now, for simplicity, for simplicity purpose, we let u be equal to f of x. So for simplicity purpose, okay, now for simplicity, let u be equal to f of x and v be equal to g of x. So you let your u be equal to f of x and v be equal to g of x. Then your du will be equal to f prime of x dx, and your dv will be equal to g prime of x dx. So substituting gives. So now what you are going to do is this. In this formula, where there is f of x, you substitute it with u. Where there is g prime, the derivative of g of x with respect to x, you substitute with dv. So this is what you're going now to have. So afterwards, then what you're going to have is that so when we do the substitution, what you're going to get is that we are going to have the integral. So in this formula, where there is f of x, we put u, then dv. Where there is g prime of x dx, we put dv. So is equal to, where there is u, we put v. Where there is where there is f of x, we put u. Where there is g of x, we put v, minus the integral. Now, where there is g of x, remember we have v. Where there is f prime of x dx, we put we put du. So this is now the formula that I'll be frequently using when we are integrating by parts, which is the integral of u dv, which is equal to uv minus the integral of v du, where u is equal to f of x, your dv is equal to the derivative of g of x with respect to x, and times the dx. U is equal to f of x, v is equal to g of x, v is equal to g of x, du is equal to the derivative of f of x with respect to x. Okay. So this is the formula that we'll be frequently using to find, to apply the integration by parts method. Okay, now we are going to look at 2 to 3 examples. We are going to look at 2, maybe or 3 examples. Then we go to integration of partial fractions. Then from there, we can call it the end of the class, which we can wait in the afternoon, where we are going to look at the application of integration. Okay, so let's look at now. The issue here is there's one issue that I need really to tell you to understand. You know, when you are integrating by parts, I hope everyone is following. Please, I hope everyone is following. So when you're integrating by parts, what becomes tedious is, or rather, the most important part when you're integrating by parts is your choice for U and also for V. So the choice that you make, if it's wrong, then you have challenges. It will be very difficult for you to do the integration, to apply the integration by parts. Again, if you make a wrong choice, you discover that that integral will not be so simpler to simplify. Now, now I'm going to show you an easy way on to use the easy procedure, or rather the easy way to recognize when you are given an integral with an integrand, an easy way to recognize which one should be your u and which one should be your dv. The choice that you make does not base on the right hand side. The choices that you make will mainly depend on the left hand side. You need to choose your u. When you choose your u, what remains is your dv. You choose for you choose your u, then what remains is your dv. So if your choice for you is wrong, then I can assure you everything becomes tedious. Yes. Okay, let's check for. Okay, so now let's look at some examples that involves now integration by parts. But before we look at that, I want you to note this. Note, make sure that you record this. So when you want to choose, if you have been given an equation, if you have been given a function that they are asking you to integrate, a combination of functions, for example, if you, let me just put it as a remark. This is a remark. How can you know that this should be my u or this should be my dv? So when integrating by parts, when integrating by parts, when integrating by parts, the functions are chosen. The functions are chosen successively in the following using the acronym, basically the acronym LIATE. So this is the most famous acronym that you are going to be using. What this acronym does is it will help you to say, when you are given a function, when you look at that function, then you say, okay, my u will be this one, my dv will be this one, using this. Now, what do these letters stand for? Maybe let me put it down so that using the acronym, let me put it down here as big as possible. We use this LIATE. What does this stand for? Each of these stands for the type of functions that you are given. The first one stands for logarithmic function. Logarithmic functions. The second one, it stands for inverse trigonometric functions. Trig functions. Okay? The third one stands for algebraic functions. algebraic functions. The fourth one, the fourth letter stands for trigonometric functions. Trigonometric functions. The last one stands for exponential functions. So all these, that's what they stand for. So we use now, for example, let me just give you a simpler example. For example, if they ask you to differentiate to find this integral, let me just. So for example, e.g., if you want to integrate the function x squared times the cosine of x. Okay, so if you want to integrate such a function, then so using LIATE, we have logarithmic functions, we have exponential functions, we have the logarithmic functions, the inverse trigonometric functions, the algebraic functions, the trigonometric functions, the exponential function. Now, if you look at this function, if you look at the function that they want you to integrate, which is x squared times the cosine of x. Now, which one should come first? Which one should be your u? If you look at the word LIATE, the algebraic functions are coming first than the trigonometric functions. So you have first the algebraic functions, then the trigonometric functions. So in this scenario, then your u will be equal to x squared. Okay? Which is the algebraic functions. The algebraic function. And your dv will then become the cosine of x dx, which is the trigonometric function. The trig function. The trigonometric function. So this is how you make your choice. You look at the sequence in the term, in this acronym LIATE, which term comes, which function will come first in this word LIATE. So the algebraic functions becomes first, then the trigonometric functions. If you have also an exponential function and a logarithmic function, then your logarithmic function like ln becomes first. For example, maybe you are given a function like e to the power x ln x. So if you look at ln x is a logarithmic function, but e to the power x is an exponential function. So if you have a function like this one and they want you to find its derivative, what you're supposed to do is your u will be ln of x, your dv will be e to the power x. If you switch them, I can assure you, if you decide to switch them, you say my u is cos x, my dv is equal to x squared dx, I can assure you, you continue integrating and integrating 100 billion times, you will never arrive at your answer. Okay, having said this, let's look at an example. Let's look at an example that involves integration by parts. Let's look at some examples involving integration by parts. Okay. Let's look at some examples involving integration by parts. Okay, so we are going to look at example number 36 of from our notes. So example number 36, example 36. The example says find the integral of x multiplied by the sine of x dx. Find the integral of cos x, x multiplied by sine x. So let's look at the solution by LIATE. Please let me ask you, which one should be our u? Let u be equal to our u will be what? If someone can just type, please, since we are learning. What will be our u? Dear students, what will be our u? That's wonderful. So our u, why is u our x? Is it because you have the solutions, or it's because you've understood what I was explaining? So following LIATE, so we have an algebraic function, which is a, and the trigonometric function, which is t. So the trigonometric function is becoming second in terms of the position. So this means our u will be equal to x. Now, when our u is x, and that means our dv will be equal to sine x dx. Okay, so this will be your u, this one will be your dv. Then, if your u is equal to x, your dv is equal to sine x dx. Okay, now if our u is equal to x and our dv is equal to sine x dx, once you do this, the next step that you're supposed to take is that you are supposed to find then our du over, you differentiate u, du dx, the derivative of u with respect to x to be 1, isn't it? Of which, when we simplify this, this is the same as du is equal to dx. And now, if your dv is equal to sine x dx, if you integrate both sides, right, what will be v? If dv, what I mean is, if dv is equal to sine x dx, when we integrate both sides of this equation, what do we get? So if dv is equal to sine x dx, and so we are saying our v will be equal to what? The negative of cosine x. How have you found this one? What you have done for you to find this one, you said you took the integral both sides. Okay, let me just do this so that for studying purpose. So, and the integral of dv, which is equal to the integral of the sine of x dx, so which will give us v is equal to the negative cosine of x. Okay. Hence, using the formula, using the formula for integration by parts. What is the formula? Our formula is the integral of u dv is equal to u v minus the integral minus the integral of v du. Okay, so this is what we have. Now, this, which is this formula, we get, now you start. So this is how we are supposed to do it. Please make sure that you follow what I'm doing on the board. So what we're supposed to do now is that, now if you look at this formula, the first thing that you did was you had to substitute where there is x by u and where there is sine x dx by dv. So what you're supposed to do is you now start substituting everything into this formula. Now this means the integral, now what is u? U is equal to what? X. That's what we said when you just started. Your u was equal to x. Your dv, what was your dv? Your dv, our dv is equal to sine x times dx. It was sine of x dx is equal to, what is your u? Our u is equal to v. Then what is our, oh sorry, not v. Our u is equal to x. Now our v, what is our v? Our v, we have solved that it is equal to the negative of cos x. So our v is equal to the negative of cos x. Then minus the integral of v, of which v is equal to the negative of cos x. Our du, what is your du? If we go back, we said let u be equal to x and dv is equal to sine x dx, then our du dx is equal to 1. This implies your du is equal to dx. So our du is equal to what? Dx. Then this will be equal to, now x times negative of sine x to give us the negative of x cosine x. Now negative times negative to give us positive, the integral of cos x dx, of which this will give us negative x times the cosine of x, then plus, now the integral of cosine of x is sine of x, but because we are taking the indefinite integral, we need to add a c. Then you are done with your integration by parts. Please, any questions if you have questions, so that and I hope everyone is following, and I hope you're able to see what I was solving. So you are done with your integration by parts. Okay, let's look at another example. So this is example number 36. Let's look at example number 37. Example number 37. So let's go to example number 37, then we'll go to example number 38. Then I'll look at one example that involves where the integration by parts is done twice, 3 times, and then we're going to end there. So I'm wrapping this part so that I can also go to the next example, which involves also integration by parts. So before maybe you ask me your questions, maybe I would like to first we first look at these examples that involves integration by parts. Then from there, that's when we can start the discussions. Okay. So this part. All right. So let's look at example number 38. So 37, you can look at it at your own time, but I need to go to 38. So we are saying find, this is example number 37. Oh yeah, 37. We are saying find the integral of ln of x dx. Just that. Find the integral of ln of x dx. Find the integral of ln of x dx. Why is the v equal to negative cos x? Because the integral of sine x is the negative of cos x. I hope with this Mwangala I've answered your question. Is it? Oh, how in the? I hope I've answered your question. I hope I've answered your question. So the v is equal to the negative of cosine x because when you have your dv, which is equal to sine x dx, for you to get, you need to find your v from this term. So to find your v, you need to integrate this. When you have your u, which was equal to x, you need to find your du from this term. You differentiate this du dx. On this one, you differentiate. On this one, you integrate. This is you are able to integrate this. It's a simpler kind of simplification. It's so simple to integrate. For under here, you need to find your v from this. Here, you need to find your du from this. So this is the only secret which is there when you're integrating by parts. Okay, now, so let's look at this example. Maybe I just need to combine this. So I'll combine example number 36 and example number 37 in one. So find one, the integral of ln of x, two, the integral of x times ln of x dx. Okay, so let's look at the solution. I'll start with one. Okay, so by the same LIATE, maybe before I even talk about the LIATE issue, maybe before I even go to that, maybe I need to give you this. Please note that the integral of ln of x dx, remember that this is the same as the integral 1 times ln of x dx, isn't it? It's the same, isn't it? Unless if you are saying it's not the same. 1 times ln of x. So if you look at this, now by LIATE, if you look at this, what you have is a logarithmic function. And 1, is 1 an exponential function, or is it an algebraic function or a trigonometric function, or is an inverse trig function? Please, I need an answer. Is 1, if you look at 1, is it an algebraic function, or is it a trigonometric function, or is it an exponential function? Answers, please. No one is responding. Okay, either way. So 1 is an exponential function. This is an exponential function. So now by LIATE, following that rule, u, which is the logarithmic function, the exponential function that at the far end, the logarithm, that's wonderful. The logarithmic function is at the beginning of this acronomy. So our u will be equal to ln of x. Now, if u is equal to ln of x and our dv will be equal to 1 times dx, so it will be our u will be equal to ln of x, our dv will be 1 times ln of x. Then, if we differentiate u, differentiating u gives, if we differentiate u, so we have du will be equal to 1 over x dx. That will be our du. Please, you can do that. And if we integrate, so for this one, you differentiate. For u, you differentiate. For dv, you integrate. So if we integrate both sides of dv, of that equation, dv, which is equal to 1 dx, if we integrate both sides, what you're going to get is your v will be equal to x, okay? Because if you find dv is equal to, it will be equal to 1. So it will be dv dx, the derivative of v with respect to x, it will give us 1, which is this one. Now, then, using integration by parts, using integration by parts, which is this formula, what we get? We get, now, so the integral, what is our u? Our u is ln of x. Our u is ln of x. Our dv is equal to 1 times dx, which is just dx, isn't it? Remember, this is just the same as dx, which is just dx is equal, which is equal to our u. Our u is equal to ln of x. Our v, where is v? V is here. V is equal to x, so it will be ln of x times x, then minus the integral. Our v is equal to x. Our du, where is our du? Where is our du? Oh, our du is here. So du is equal to 1 over x dx. So where there is du, we substitute by 1 over x dx. So du is 1 over x dx. Then this will give us, so we can rewrite this as x ln of x minus the integral. Now x and x will cancel, so it will be 1 dx, which will give us x times the ln of x minus, now the integral of 1 with respect to x is x plus c, which is the constant of integration. So then you are done with your solving. That's the end of your solving. Okay, now maybe after having said all this, I would love you to go try this one. Please try it and see what you can do. The solution is already there on the board, and even if I try to solve it, because the procedure will be the same, wherever there is one, so if you look at this, so we have an algebraic function and a logarithmic function. So we have an algebraic function and a logarithmic function. So in short, if you look at LIATE, it means that our algebraic function, our logarithmic function, which is the ln of x, will be our u. Our algebraic function is in the third position, it will be our dv, isn't it? So the solution is already there, unless if you want me to do it, but let's do it. Yeah. So but you can. So I'll leave part 2 as an exercise. Now let me just leave it as an exercise. You can manage to handle it. Now from what we've done, we've seen a situation where you just integrate by parts once. You just do a single integration by parts and then the answer comes out. Now, we have situations where the integration by parts has to be applied twice, thrice. So there are these functions which are so a bit tricky. When you are applying the integration by parts, you discover that for you to apply the integration, for you to arrive at your final answer like this one, you have to apply the integration by parts more than once. Maybe 2 times or 3 times or 4 times or 5 times. You continue integrating by parts. Again, you apply integration by parts. You apply integration by parts up to the time you're going to arrive at your answer. So those are the functions. This is the next example that you're going to look at. So the next example that you're going to look at is a situation where this given function, for you to arrive at its final answer, you have to apply the integration by parts twice or 3 times or 4 times. Okay, so let's look at this of which this is example number 30. That was supposed to be 39. Even though in your notes, I think it's showing as if it's example number 4, but it was supposed to be the case. Okay. So let's look at example number 39. Okay. So find I'll say I'll add the two of them. Find one, the integral of x squared sine of x dx. 2, the second one, make sure that you follow what I'm writing on the board. The second one, which will be the last one of our session today, as of today, this is the last one under integration by parts. The second one is the integral of e to the power x times the cosine of x dx. This what is in your notes? There is a sign here, but I've changed. If you can check, I've changed the questions. So please make sure that you follow what I'm explaining on the board. Otherwise, you have challenges. So make sure that you follow what I'll be explaining on the board, because I've changed the questions a bit. So let's look at the solution. So like I mentioned, there are situations whereby you have to apply the integration by parts more than once. So in that situation now, what kind of questions do we have that we are forced to apply integration by parts? And remember, when we just started, I mentioned to say, for you to apply integration by parts, is you can only do that when you see that, or you have exhausted all the methods for integration by parts. You have tried to use the substitution method, it's failing. You have tried to use the identity, where the substitution of integration, where you use the identities, it has failed. You try to do the substitution of inverse trigonometric functions, still it's failing. Then if all these are failing, that's when now you can think of integration by parts. But there are at times when, even if you don't try those, you just look at the question to say, this question, for me to be successful in terms of simplifying it, I have to apply integration by parts. So you have all these scenarios on your disposal. You decide, you make a choice from there. Now let's look at the first one. The first one is the integral of x squared times the sine of x dx. Let's look at this one. Now, by LIATE again, if you apply this method, this acronym is very, very important. If you go can assure you, try. I would wish you to go try to switch with the substitution that I'm making using this acronym, and then you see where you can go. Basically, now in maths, when you are doing maths, you're not supposed to believe everything that you are taught. Okay, that's why there's a course called real analysis. This course, it reveals the truth about something, the truthfulness of something, or even what we call number theory. It reveals the truthfulness of something. Just because someone told you that 1 plus 1 is equal to 2, you already know that is the 1 plus 1 is equal to 2 forever. No. Suppose if I say 1 plus 1 is equal to 3, 1 plus 1 is equal to 1. So every time when you're given something, try to do it the opposite, and then you realize so that you prove it to say, okay, what this person was telling me was the truth. Okay, now let's look at this question. Then, so by LIATE, we have logarithmic function, inverse trigonometric functions, or algebraic functions, trigonometric functions, exponential. So algebraic becomes first, isn't it? So our u will be equal to what? X squared, and our dv will be equal to the sine of x dx. Then, when we differentiate du, we are going to have du will be equal to 2x dx, and if we integrate dv, the equation dv which is equal to sine x dx, we are going to get our v will be equal to the negative cosine of x. Okay, now integration by parts gives, so from the formula for integration by parts, from this formula, the integral of u dv, which is equal to u v minus the integral of v du, what we are going to get is this. So what we're going to have is the integral, our u is equal to x squared, our dv is equal to sine x dx, which is equal to our u is x squared, our v is the negative of cosine of x minus the integral, our v, where is our v? Our v is the negative cosine of x. Then our du is, sorry, you can't see what I'm pointing. So our du is equal to 2x dx. So our du is equal to 2x dx. So times 2x dx. When we simplify this, we are going to have x squared, the negative of x squared times the cosine of x. So negative and negative will have plus the integral. So because 2 is a constant, basically we can just factor it out. 2 times the integral of x, the cosine of x dx. Now the question is, have we arrived at our answer? No, we've not yet arrived at our answer. So then what are we supposed to do? What we're supposed to do is, we are supposed to integrate again by parts. So we integrate, so you see, we are saying the integral of x squared sine x dx is equal to x squared is equal to negative x squared cos x plus 2 times the integral of x multiplied by cos x dx. So this function again, we cannot integrate it directly. So you integrate this integral, that part. Again, you do what? Integrate by parts. Again. So you integrate by parts again. So this is what you're supposed to do. Now, so we need to integrate by parts this part. So to do that, let's extract it. Let's extract that part. We integrate it by part alone. So we need now to integrate by parts this x cos x dx. So we need to integrate by parts this part. So after when we integrate it by parts, so because this part, there is a part that we need really to integrate by parts for us to arrive at our answer. For this one, so again following LIATE, again by LIATE, our u is equal to x and our dv will be equal to the cosine of x dx. So our du, so the derivative of u with respect to x to give us 1, so that when you simplify, you are going to get our du is equal to 1 dx, and our v, the integral, when you integrate both sides of this equation, what you get is the sine of x. Hence, if you integrate by parts, hence, if you apply integration by parts, hence, by this formula, which is the integration by parts formula, uv, which is equal to minus the integral of v du, we are going to get, now, the part that we are now integrating by parts is not the old part, it's this new integral that has resulted from what we are doing. So this new integral that has resulted from what we are doing is the one now we are going to apply again integration by parts. Okay, so our u in this new integral, so we have the integral. So we have the integral. Now our u, so it's the integral. Our new u now is equal to x. Our dv is equal to the cosine of x dx. Our u is x. Our v is sine x, which is our new v here now, minus the integral. Our v is sine x. Our du, what is our du? What is our new du? Our du is equal to dx. When we simplify this, we are going to get x sine x minus the integral of sine x is the negative of cos x. So plus c. Now, this when you simplify it, we get x sine x plus the cosine of x plus c. So what you have done, you've not yet completed your integral here. What you have done, you have just decided to extract this part to evaluate the integral of this part using integration by parts. Now, what you're supposed to do now is that then you're not supposed to bring all these to what you have found here. So you substitute where there is the integral of x cos x dx, you substitute it by this expression. That's the integral of x squared times sine of x dx, which is equal to x squared. It was equal to the negative, which is equal to the negative of x squared times the cosine of x plus 2 times the integral of x times the cosine of x dx, isn't it? So then now this one will be equal to the negative of x squared times the cosine of x plus 2. Now, after this 2 is a constant multiple. So now, where there is the integral of x times the cosine of x dx, you substitute this. So it is x times the sine of x, then plus the cosine of x plus c1. We can call that one, we can call this one to be c1. When we expand this, what you're going to have is so when we expand this, what you're going to get is that when we expand, so this is just equal to negative x squared times the cosine of x plus 2x times the sine of x, then plus the cosine of x, plus 2 times the cosine of x, then plus the last one, c. So this is now your final answer. So that is the final answer. Okay. So there is 2 the cosine of x. Okay. Let's go to the last one about this example. So from this, I'm going now to go to, before 11 hours, I'll go to integration by partial fractions. So the example that I'm about to solve is the last one. So please, let's try to hold on so that we can finish our examples as of today. We can also do integration so that in the afternoon we'll just look at some applications of differentiation or integration. Then tomorrow we'll be revising. Okay. So here, maybe there are some of you who don't have the notes, right? And you just see me writing few statements and then start solving. Please make sure that you download the notes on Moodle. All the notes are on Moodle, or you can get from your friends. Because what I'm doing, I'm just sampling some of the questions from the notes and examples in the notes which are already on Moodle. I don't need to write all the things which are in those notes because you already have them. All I need is just to go through, and then do some examples from those notes, and then that's the end. Okay, now let's look at the last one, which is number 2 from of this session, part 2 of the solution. It's the integral of e to the power x times the cosine of x dx Again, if you apply LIATE, if you apply LIATE, if you apply LIATE, if you apply LIATE, our U will be equal to what? Logarithmic function, inverse trigonometric function, algebraic function, trigonometric functions, exponential function. Our U will be equal to the cosine of x, and our dv will be equal to e to the power x dx. Then, when we differentiate this, our du dx will be equal to negative sine of x, and this means that our du is equal to negative the negative sine of x dx. And if we integrate both sides of e, remember e to the power x is a very special function that when you differentiate it to get the function itself, you integrate it to get the function itself. Are you able to see? Okay, so now, and our v, when you integrate e to the power x, you get e to the power x. Hence, by the formula, by integration by parts, which is the formula, the integral of u dv, which is equal to u v minus the integral of v du, we are going to obtain that. What are we going to get? Now, we are going to get the integral. Now, what is our u? Our u is cosine of x. Our dv is e to the power x cos x. So we have e to the power x cosine of x dx, which is equal to our u is the cosine of x, our v. So we have the cosine of x times e to the power x minus the integral. Now, minus the integral, our v is, where is it? So our v is e to the power x. So we have e to the power x. Our du is equal to negative sine x dx. So negative sine x dx. So then when we simplify this, this will come to be e to the power x times the cosine of x. Now negative and negative to give us positive. The integral of e to the power x times the sine of x dx. Again, if you look at our expression on the right hand side, we have an integral, which is the integral of e to the power x sine x dx, which we cannot differentiate as simply as possible, which we can simply differentiate there and then and find the answer. Instead, we have again to apply integration by parts. So, applying integration by parts again. Now this time, so we just, which is that is on e to the power x sine of x dx. So we apply it on this one. Again, we let our u. Our u again is going to be equal to the sine of x, and our v is going to be, or our dv, not v, our dv is going to be e to the power x dx. So then our du, the derivative of u with respect to x is equal to cosine of x, because the derivative of sine of x is cosine of x. So when you simplify, you're going to get the cosine of x dx. Okay. So what I was saying is we apply integration by parts again. Or now, this time around, we apply the integration by parts on the right-hand side on e to the power, on the integral of e to the power x sine x dx. Now, in this scenario, in this case now, what we're going to have, our u will be the same as the trigonometric function sine of x, and our dv will be equal to e to the power x dx. Then when you differentiate u with respect to x, you're going to get du is equal to cos x dx. And the derivative, when you integrate this, here you need to differentiate. In the other part, when you integrate the dv, which is equal to e to the power x dx, you integrate both sides. What you're going to get is your v will be equal to e to the power x. Hence, when you substitute, hence, from the integral of u dv, which is equal to uv minus the integral of v du, which is the integration by parts formula, what you're going to get is that we get the integral, now our u in this case is sine x, our dv is e to the power x dx. When you multiply those two, you're going to have e to the power x sine x dx is equal to our v in this new, our u is sine x. So we have sine x times our v is e to the power x. Okay. Then minus the integral, our v is e to the power x, our du here in this case is the cosine of x dx, which will just be equal to, when we rewrite it, e to the power x sine of x minus the integral of e power x cosine of x dx. Now, so what you're supposed to do now, when you started, you said the integral of e, the integral of e to the power x times the cosine of x dx is equal to the cosine of x multiplied by, is equal to e to the power x multiplied by cosine of x, then plus the integral of e power x multiplied by sine x with respect to x. Now, you need to, or substitute where there is the integral of e to the power x sine x dx, you need to substitute it with e to the power x sine x minus the integral of e to the power x cosine x. Okay, so hence, okay, so I'm rubbing the upper part. Hence, now this means now the integral the integral hence so the integral of e power x times the cosine of x with respect to x is equal to e power x times the cosine of x plus that the integral e power x times the sine of x dx, which is equal to e power x times the cosine of x plus the integral of where there is the integral of e power x sine of x dx, we substitute it with this term, which is equal to e power x the sine of x minus the integral of e power x times the cosine of x dx, which is an equation in e, which is an equation so if you look at that expression, you have the integral on the left hand side, you have the integral of e power x cos x. On the right hand side, we have e power x cos x plus e power x sin x minus the integral of e power x cos x dx. Now, if you check what we have two things here which are appearing to be common. We have this, the integral of e power x cos x dx, and also we have the integral of e power x cos x dx on both on the left hand side and on the right hand side. So rearranging, if we rearrange this and simplify, rearranging, so rearranging, when we rearrange this, what we are going to get is, so we are going to have the integral of e power x times the cosine of x dx. This e power x cos x dx, of the integral of e power x cos x dx will go on the, we add it both sides so that we can get rid of that, plus, so we have again another integral of e power x cosine of x dx. Then on the right hand side, we are going to remain with on the right hand side, which is equal to e power x cos x plus e power x sin x. Now, the integral of e power x cos x dx plus the integral of e power x cos x dx, this will give us, which will give us 2, the integral of e power x cos x dx is equal to e power x cos x plus e power x sin x. But have we found our integral yet? No. We need to simplify further. From here now, we now say, we now conclude, therefore, thus, when we simplify, thus, when we divide both sides by 2, what we're going to get is e or x. The integral of e or x cos x is equal to 1 over 2 multiplied by e power x cos x plus e power x sin x. Then you have done with your integration, of which if you want, you can put, say, e power x over 2 multiplied by the cosine of x plus the sine of x. Okay. The test will be on Monday. Monday. To prepare. That's why tomorrow we are meeting for revision. There will be 20 questions, 1 hour, 30 minutes. 20 questions, 20 sampled questions. So I have about 2,000 questions, which is multiple choice and one word answer combined, 2,000 questions. So when you open, when you start the test, it's forward, no backwards. You can't go forward without answering this other one. And once you go forward, you can't go backwards. So please make sure that you find where there is a strong internet. Okay, so that's the end of this example. Sorry for that. The camera isn't where it's. I don't know what's happening to this camera. Okay. So let's look at the last part of today's session, which is partial fractions. So some of the examples that I've left behind, please find time to go through them. Now, the last part of this session is partial fractions, integration by partial fractions, which is the last part of integration. Okay, let's look at the last part of integration of rational functions. So, which is the last integration of rational functions, has been the last part of today's session. Integration of rational functions. Okay, so there are some functions that you can't integrate, there are other functions that whether you try to use the substitution method or you try to use integration by parts, or you try to substitute trigonometric functions, or you try to substitute, you try to bring in the idea of trigonometric identities, or you try to bring in the idea of inverse trigonometric substitution, still you realize that it will not work. So in such a scenario, such functions are functions such as the rational function. You know, when you have a rational function, there are two things. It's either a rational function of trigonometric functions, or a rational function of algebraic functions, or a rational function of exponential functions. So if you have such a scenario, you try this way, you try that way, it fails, especially rational functions which are generated from algebraic functions. So what you need to do is you apply the integration by partial fractions. Now, how do we do that? Let's look at an example. So I don't need to mention a lot of things here. What I've explained is more than enough. So let's look at this example that involves the idea of integration, where we apply the partial fraction. All right. So this is example number 40 from your notes. This is example number 40 from your notes. So please, you can check from your notes. You have this example with you. Now, so example 40. I'll also do only two examples today under this part. So only two examples, those will be more than enough for us to grasp the concept. So after once you just grasp the concept, then that's it. Because the rest of the examples is just a repetition of what we have already gone through. Every one of us also has ever done partial fractions. So I don't need to have waste time on how to compute using partial fractions. Okay, now even as you be writing the test, if there's a question that comes on that part, make sure that you first reduce it to partial fractions and then you integrate it. Please, let's go through whatever we've learned in the past 2 weeks. Go through properly. That's why I've pushed the test to Monday. So you have the entire weekend on your disposal to go through just maths. You have Friday, Saturday, Sunday. Monday, you should be ready. Please find somewhere where there is strong internet. I don't like those unnecessary calls that you make, some of you. Even if you try once, then it fails, and then you start saying no internet. If you say Moodle, yes, but if you say bundles, please, that one, that's what I'm explaining to you to say on that day everyone should be ready. Don't take a chance. I will not give any makeup. Okay, now let's look at this one. And those who are fond of just missing unnecessarily in the name of having a makeup, there will be no makeup. Okay, so let's look at this one. This question. The question is saying, find the integral of 5x plus 4 divided by 2x squared plus x minus 1 dx. Solution. If you look at this, the integrand, what method can you use to integrate here? What method can you use to integrate? Is the camera still faint? So what method? You try substitution, it will fail. You try whichever method that you can try to maneuver around with, it will still fail. Henceforth, we need to use integration by partial fractions. Now, to do so, the first thing that you need to do is the first thing that you need to do to express the integrand, you need first to express this integrand, which is inside into partial fractions. So to find the integral of 5x plus 4 over 2x squared plus x minus 1, we first write, we first express the integrand x plus 4 over 2x squared plus x minus 1 into partial fractions. So we first express this as a sum of partial fractions. Okay, so you first express it as a sum of partial fractions. Now, in partial fraction form, our integrand, which is 5x plus 4 divided by 2x squared plus x minus 1, this is just the same as 5x plus 4 over, when we factorize the denominator, it's going to give us, when we factorize the denominator, it's going to give us x plus 1, then x minus 2. So this is what we are going to get. Oh, sorry. We have 2x minus 1. So this is what you're going to get. Now, in two partial fraction, then this becomes, please make sure that you 3 over x plus 1 plus 4 over 2x minus 1. Okay. After you do that, then hence, so what you are saying is the integrand 5x plus 4 divided by 2x squared plus x minus 1 is the same as 3 over x plus 1 plus 4 over 2x minus 1. Hence, then now, you say now the integral of 5x plus 4 over 2x squared plus x minus 1 with respect to x, this is the same as the integral of 3 over x plus 1 plus 4 over 2x minus 1 with respect to x. Using the linearity property, this is equal to the integral of 3 over x plus 1 dx plus the integral of 4 over 2x plus 1 dx, minus 1. Okay. Now, when you reach this stage, you can either use the substitution method or you can just go directly. That's not a big deal. But this is the solution is already there in your books. In your notes. I'll just explain it. I'll not write much so that we can save time. Okay. Now, if you look at the resulting partial fractions, 3 over x plus 1 and 4 over 3x minus 1, we can integrate this. They are so easy to integrate as compared to the previous one. when we just started. These partial fractions are very easy to integrate as compared to what we started with. Okay, now, so now let's look at the final part. So, when you look at what we have arrived at, if we integrate by the substitution, when you reach this stage, at first you were unable to integrate using the substitution method, but here now you can now integrate using the substitution method if you want, or if you don't want, that's not a big deal. But the more you practice, you realize that when you just look at the question, you'll be able to tell, okay, this is equal to this and this is equal to this. But as at your stage, let's do this. So we need to integrate by parts and on this one, or both. You can integrate by parts, by the substitution method, sorry. You integrate this using the substitution method. You can also integrate this using the substitution method. Okay, then by substitution method, okay, so for this integrand 3 over x plus 1 dx, let our u be equal to x plus 1, then our, let me just put this as 1, or just say for 1, then our du will be equal to dx. So the integral of 3 over x plus 1 dx is just equal to the integral of 3 over u times du, which will give us 3 ln of u, we'll just say plus c1, which is 3 ln of what? Our u was equal to x plus 1 c1. Okay. 2 for the integral of 4 over 2x minus 1 dx, we let again our u be equal to 2x minus 1. Then our du dx will be equal to 2. When you simplify, it will give us du is equal to 2 dx. From there, then we have so what we're going to get now is that the integral of 4 over 2x minus 1 dx is equal to the integral of 4 over u multiplied by, now the dx, we are going to substitute with o. So what I was supposed to write here is that our du is equal to 2 dx, which will give us, which will imply dx is equal to du over 2, okay, something like that. So we have du over dx. So this will be equal to, sorry, du over 2, sorry for that. So and this will be equal to, we have 2, so this is equal to, so the 2 times the integral, okay, 2 over u du, which will be equal to so this will give us this, and this is equal to 2 ln of u plus c2, which is equal to just 2 times ln. Now, in this case, our u was equal to 2x minus 1, then plus c2. Space here. Okay, let me do this. Yeah, so which is equal to 2 ln of 2x minus 1 plus c2. So what you have done, after you had split that integral, after you had split the given function, you have written it as a sum of integral, as a sum of partial fractions. Then you took the integral of that fraction, which was equal to the integral of its partial sums, the sum of the integral of its partial sums. Then you discovered that each of those has given you some value. Then now, therefore, what you're supposed to do now, you combine all. Therefore, we are saying the integral of 5x plus 4, was it 5x plus 4 minus 4? 5x minus 4 divided by 2x squared plus x minus 1 dx, which was equal to the integral of 3 over x plus 1 dx plus the integral of 4 over 2x minus 1 dx. This will be now equal to, now the integral of 3 over x plus 1 dx, we had found it to be 3 ln of x plus 1 plus the integral of 4 over 2x minus 1 dx, we had found it to be 2 multiplied by ln of 2x minus 1 plus, sorry, we're supposed to have, this is equal to 3 ln of x plus 1 plus c1, then plus, so plus c2. Okay, when you combine this and simplify, you have 3 ln of x plus 1 plus 2 ln of 2x minus 1, c1 plus c2, it will just give us c. Then you have completed your solving. When you convert into partial fractions, please, can you do the partial fractions conversion? Someone is asking where is the 3 coming from. Try to convert it into partial fractions and then okay, you mean the 3 is not coming? Oh, okay. All right. All right. Let's look at another example. I think this will be the last example. about. Please, you need to look for typos if there are typos there, so that I don't go astray. Another person is saying the 4 is not coming out. Which one is supposed to come out? Is it the 4 or the 3? Please, you need to clarify so that we will be on the same page. When you do partial fractions, what do you get? Supposed to be 3 over x plus 1 plus 1 over 2x minus 1, isn't it? Okay, I'll give you that as a food of thought, please. I don't even know where I started from, so just go and handle it. I don't know whether we're supposed to have this 4 here, because from my partial fraction solving, this 4 is not here, so I'm not so sure how this 4 came about. Either way, I think this 4 is not supposed to be here. Can you respond, those who have managed to express it into partial fractions? This 4 is not supposed to be there. Sorry for that. That's a mistake. There was supposed to be a 1. Yeah, not really the 4. So here we have a 1. Sorry for that. I've just seen that. So we have a 1. Then we're supposed to take out this. So what we're supposed to have here is the 1 over 2, not 2. So 1 over 2, sorry for that. So we are supposed to have the 1 over 2 here. And lastly, the 1 over 2. Please, did you do the simplification and then see where we went wrong, and then you just need to verify, please. Okay, but either way, from the look of things, you've understood how to handle a question that is involving partial fractions. The main part something that you need to do is you need to understand, you need first to express the given fraction into partial fractions. I mean, as a sum of partial fractions. Let's look at the last example, which also involves partial fractions as well. Okay. Okay. Let's look at the last example of today's session. Which is example number 41. The example says determine the integral so the example says determine the integral of 3x squared plus 16x plus 5 plus 15 divided by, okay, x plus 3 squared dx. I'll be fast. Solution. So into partial fractions, partial fractions, the integrand becomes now our integrand is 3x squared plus 16x plus 15 over x plus 3. Was it squared or power 3? Yeah, power 3. It's power 3, please. Into partial fractions as a sum of partial fractions. This is equal to 3 over x plus 3 plus 2, or minus, sorry, minus 2 over x plus 3 squared plus 6 over x plus 3 the power 3. Hence, hence, hence the integral hence the integral of 3x squared plus 16x plus 15 divided by x plus 3 cubed. This is just the same as the integral of 3 over x plus 3 dx minus the integral of 2 over x plus 3 squared dx plus the integral of the function 6 over x plus 6 squared dx. Okay. So if you look at all these questions, they are involving x plus 3, x plus 3, x plus 3. So now, by substitution method, let u be equal to x plus 3, and so du will be equal to dx. Hence, the integral of 3x squared plus 16x plus 5 over x plus 3 power 3, which is equal to the integral 3 over x plus 3 with respect to x minus the integral of 2 over x plus 3 squared dx plus the integral of 6 over x plus 3 power 3 dx. This is just the same as, this is just equal to this is just equal to Now, by the substitution, the integral of 3 over u, because 3 x plus 3 x, because x plus 3 we have substituted being u, and du is equal to dx. So we have du plus, minus the integral of 2 over u squared du plus the integral of 6 over u cubed du. Okay. So then this one then becomes the let me do this. This one then becomes 3, the integral of 1 over u du minus 2, the integral 1 over u squared is u to the power negative 2 du plus 6 out, the integral u power 3 power negative 3 du. Now, using those formulas for integration, applying those formulas for integration, then we are going to get this will be equal to 3 times ln of u minus 2 times u power negative 1, okay, because over negative 1, because you add the power, it will be negative 2 plus 1 over negative 2 plus 1 to give us negative 1 plus 6 times u power negative 2 over negative 2, then plus c, which will give us 3 ln of u minus 2. So negative and negative to give us positive over u, because u to the power negative 1 is 1 over u. Positive and negative to give us a minus 3 over u squared plus c. Now, our u sorry. Okay. So now, our u, we replaced u to be what? So this is equal to, this is equal to 3 ln of x plus 3, because our u is equal to x plus 3, then minus 2 over x plus 3, then minus 3 over x plus 3 squared plus c. Then you say you have found the derivative of the function of the integrand 3x squared plus 6x plus 15 over x plus 3 to the power 3. So this is your integrand, which is here. So, unless if you have questions for me, otherwise, this is the end of the session. I'll be able to let you know before lunchtime. Uh, Maybe just to cut it short. To cut it short, this is 11:30 something. So I'll be able to let you know by 13 hours, but let's try to meet at around 14. We look at some applications of integration. Then we can call it the end of the calculus. So let's touch some parts for applications of integration. But for integration, I think we are done. This is the end of integration. So we just need to look at now some applications of integration and some applications of differentiation, which I believe in the afternoon we'll be able to finish up that. Okay, thank you so much. We'll just meet from 14 hours to 16 hours for just 2 hours again. Then we can call it the end of the session. So otherwise, thank you very much for all those who attended, and have a nice lunch as we all go for lunch.